Hi, I'm Matthias Heinrich, and it's my pleasure to be here and present to you our joint work with Alex and Christoph from the University of Lübeck and Lasse from EcoScout on large-scale deformable 3D registration using a differentiable volumetric rasterization that makes 3D point distances extremely fast, robust, and accurate. It also improves differentiability and scales to clouds well beyond 100,000 points. Point cloud motion is ubiquitously used for autonomous devices, human motion tracking, and medical image analysis. Point clouds provide a more efficient and privacy-preserving representation of a 3D scene, which makes them suitable rather than volumetric grids. However, defining a 3D distance on sparse point clouds for training a learning-based model or using it in instance optimization is very tricky. For chamfer distances, we firstly need to compute nearest neighbors between points in the target and source cloud points in every iteration, which does not scale well. And secondly, we can only obtain unstable gradients with respect to the moved coordinates. We propose to perform an intermediate rasterization of the coordinates by efficiently accumulating partial volume contributions in a grid based on trilinear extrapolation. DiffRock scales well for large-scale point clouds and can be used as a drop-in replacement for chamfer or earth movers distances. It also enables us to efficiently regularize and extrapolate the initial sparse 3D point cloud fields. And in contrast to binary occupancy grids, we obtain a grayscale surface representation that enables backpropagation and well-defined derivatives. Check out our GitHub implementation for details, which shows how to efficiently employ the Jacobian operator of the grid sample function in PyTorch. Our method comprises of three main parts: a geometric registration model, which could be either a point PW CNet or a customized DGCNN with edgeconfs that predict a sparse motion vector field for about 8,000 points. Our new DiffRock regularizer that performs an intermediate densification and B-spline smoothing, and that is more robust than KNN smoothing that is used in prior work. And finally, our new DiffRock point cloud distance, which enables stable gradients and scales well to huge datasets. We experimentally validated our method's contributions on the PVT 1010 dataset, which is a large 3D lung volume dataset for registering inspiration and expiration scans of COPD patients. We set new state-of-the-art performance by employing our DiffRock approach for unsupervised or self-training together with instance optimization. This highly accurate ADAM instance optimization particularly benefits from the efficiency of DiffRock, which is up to 1,000 times faster than chamfer for already moderately sized clouds, and also more memory efficient. Our ablations show improvements through replacing chamfer distances or an alternate approach that first rasterizes the cloud and then warps the volume, spatial transformer loss. And a further gain is achieved by retraining the model on its own predictions. More visualizations and a standalone demo for your own data, for example human 3D poses, is available at Hugging Face Spaces. To conclude, we have presented a new way of computing point distances in large-scale point clouds and demonstrate its effectiveness for learning and optimization-based 3D registration. Check out how we want to translate this new research into 3D surgical tools with ultrasound guidance at EcoScout AI, or see our open PhD and postdoc posts, as well as details of implementation and dataset on GitHub. Thank you very much for listening.